In this video series, we're talking about regression with different variable types, namely categorical and quantitative variables. So we're having a mixed variable design. And in the previous videos, we set the stage by reviewing analysis with a categorical variable, with a quantitative variable, and then also looked at interaction. And now it is time for the main event. That is the analysis of covariance. This is frequently referred to by the acronym ANCOVA. In order to conduct an ANCOVA, you must have at least one categorical factor and at least one quantitative variable. And we're going to start with this simplest situation where we have a single categorical variable and a single quantitative variable. In order to conduct ANCOVA using the classical method, which is what we're going to explore, we assume homogeneity of regression slopes. That is, we assume that the covariate is not interacting with the explanatory variable in the effect on the response variable. So that when I ask the question, what is the influence of the quantitative covariate on the response variable, you don't have to say it depends upon the levels of the factor because it is the same regardless of the levels of the factor. There are ways to dealing with non-homogeneity of regression slopes, but they are more complicated, and I actually teach those in a more advanced course than this one. So we're going to stick with classical ANCOVA and get the feel for what this is all about and why we do this. And the goal I've listed here is to compare the effects of groups after adjusting for the covariate. You're used to, in multiple linear regression, if you watch the past videos, you know that we did compare the influence of one quantitative variable on the response variable after controlling for or adjusting for the other covariates, the other quantitative variables that were in our regression equation. So now it seems to make sense that we go ahead and do the same thing when we have a categorical variable and a quantitative variable, namely that we look at the effects of the categorical variable after controlling for the effects of the quantitative variable. And that is indeed the goal of analysis of covariance. So throughout the remainder of this video series, I'm going to work on an example. The data are actually real. I obtained these data as real data from a source that I have not been able to track down and find what that source is, so you'll have to consider this an unknown source, but real data. And what the purpose was of the study was to look to see if income is related to race. Now, the term that I'm using here is race, but as you'll see, we have some racial and some ethnicity in our categorical factors, so just bear with me as I just use those terms rather interchangeably, even though they do not mean the same thing. I'm going to use them interchangeably here so I don't have to keep describing the difference each time that we do it. But we basically are going to look at three different race/ethnic categories here. One is black, one is Hispanic, and one is white. So we call this ethnic income data, and we're looking at the relationship of income to race. That is, do we see differences in income levels for members of these different categories? Do we find differences? That would be an important question to examine, and it is the one we're going to examine here. Now, in addition to having a grouping variable, a categorical variable with these three different racial/ethnic groups, the data also includes not only our response measure, which is income, but also a potential covariate, and that is education. If you think about it, the amount of education you have probably influences income, and so we may want to consider that in our analysis. But the first thing I'm going to go ahead and do is read in the data and create the factor for my categorical variable. The data when I read them in, actually has B, H, and W for my levels. Those are characters. R would consider them just characters. I need to tell R that these are factors. So even though they're not numbers, in order for everything to behave appropriately in my analysis, I need to convert this into a factor, a categorical variable. And so that's what I'm doing here. Let's take a look at this. So I have my income. Now the income is given in thousands of dollars. So 16 would mean 16,000. Similarly down here on line 20, I see a 58. That would be 58,000. And then the education is years of education. And then you can see that we have these various categories in which we have Black, Hispanic, and it looks like more white than anything else here in our data set. So let's look at a box plot to illustrate the income differences. If you had simply had income and race in your data set and did not have education, you would probably consider doing a one-factor analysis of variance, that is, multiple regression with one categorical explanatory variable and one quantitative response variable. And we would start by making a picture like this. And the picture shows us the differences in income levels. When I look at this picture, I see that it's similar in terms of the range and the interquartile range for Black and Hispanic, although Hispanic have a higher median income. And then with white, there's much more variability. Reaching up, that interquartile range actually extends well above the interquartile ranges of the other two categories. And you can see we even have some outliers here that are quite high. And we also notice higher variability. This whole picture here of this box plot is more variable. So at this point, I'm only looking at the income as a function of race. I'm ignoring education. And consistent with these box plots, let's create some descriptive statistics down here. I won't go through the commands that I'm using because we have seen these multiple times in previous videos. So I'm going to go ahead and just run this and look, and we have everything you see in the box plots, plus additionally we have a mean and standard deviation. Focusing on both the medians and means as the centers of our distribution, I can see that there is a higher income, both median and mean for white, although I notice the mean is quite a bit higher than the median because we have this skewed distribution. Notice that above the median on this box plot, it extends substantially further up than it does below the median. So because of that skew, the mean is drawn in that direction. But even if you ignore those outliers by focusing on the median, we have about $7,000 per year more for white than we do for Hispanic, and looks like about $13,000 more for white than we do for Black, and about $6,000 more for Hispanic than for Black. So this is what we see based upon these particular sets of data. I wish I could tell you where this sample came from, not just the source of the data, but whoever did the research, where they actually obtained the individuals for this study. That's obviously very important. So I'm not going to do any write-up that I'm going to go publishing based upon this study because I don't even know how the sample was selected, where it came from. But for the purposes of pedagogical understanding of ANCOVA and the techniques, we can go ahead and move forward with this data set. I note in the standard deviations here that the variation is similar with Blacks and Hispanics. We saw that in the box plot, but a great deal more in the white condition. Now, if we treated this as a one-factor design, where race is the factor and income is the quantitative response variable, we would check our conditions for valid inference. We would check to see if we have homogeneity of variance of the residuals and normality. I can already tell you I very much doubt, looking at this picture up here, that we're going to have homogeneity of variance, and also looking at these standard deviations. But let's go ahead and look at it as a predicted residual plot, which is typically what we do to get started. Here's the residual versus the fitted values. And sure enough, you can see over here in this third group that wide variation compared to the two groups. So there's a big problem with our condition of variance equality. So we're not going to be able to trust our inferences. Let's proceed knowing that we're not going to trust those, but we're going to do this for learning purposes. And let's look at the normality of our residuals. And again, no surprise, these are not normal. They are right skewed data. Why am I not surprised? Well, one of the common examples that statistics teachers use to teach the concept of skew is to look at income data, because it's very common when you look at income data to find that there's a clustering around some middle point of income, and then there's a skewness in the positive direction as fewer and fewer people earn higher and higher dollars. So I've not met either of the conditions for valid inference here, but we're going to plunge forward because we're in a statistics class. If we were in a research project, we would not plunge forward. We would not make any inferences. Now, that's not to say that we couldn't still talk descriptively about what we're seeing here and take those descriptive statistics and say quite a lot about what we're seeing in our sample. But in terms of taking this and saying, is it stable enough to infer outside of our sample, we really are not going to be able to do that given we've not met the conditions for valid inference. So we'll either stick with description or perhaps go and learn some robust or some non-parametric methods in order to analyze these data. Let me go ahead and do the ANCOVA table, even though we're not going to trust that p-value. If we had met the conditions for valid inference, we would say, assuming a maximum type 1 error rate of 0.05, we would say that we're able to reject the null hypothesis of mean equality. And the differences in means that we see in our sample, we would infer that there are differences, not necessarily the same differences of what we're seeing in our sample, but that there are some differences in means outside of our sample if we were to take additional samples or make inferences back to the population if this was a sample that was chosen at random, which may very well not be the case. But we still are looking at the p-statistic about making inferences outside of this study. Can we expect to see outside of this study that there are differences? Not the differences we observed, but that there are some differences in the means. Again, though, we're not going to do this here because we've not met the conditions for valid inference, but that's what we would do if we had met those conditions for valid inference. So we can't say much based upon our findings. If the conditions had been supported, we would have concluded that there are income differences for different racial or ethnic groups. We saw that in our sample means, and we're wanting to know if we can infer these results beyond our study. We cannot, but that isn't because of the size of the p-statistic, but rather the fact we cannot trust that p-statistic. Okay. So we have an obvious extraneous variable, and that is education level. It probably is going to help us out if we include that in our study. So I'll take up that topic in the next video.